disposal. All right, so beta is our basis for vector space V. For each x in V, there's just a unique set of scalars, C1 through Cn, such that linear combination, right? It's always linear combination. So if beta is a basis for V and x is in V, then the coordinates of x relative to the basis, or the beta coordinates of x, are the weights, C1 through Cn, that make up that linear combination. All right, so what that's really telling us is that you have basically transformed coordinates. And linear transformations really do this for us, which is why we studied that. All right, so what we're dealing with is the idea that if you're living in the world of I and j, 1, 0, 0, 1, then the coordinate 1, 2 means exactly that, over 1, up 2. But if you're living in a world where your basis vector is something like, oh, well, here, 3, 2, negative 4, 1. What that's telling you is that the value of every movement in x is really 3, 2. And every movement in y is really negative 4, 1. It's really kind of interesting to think about. But if you think about it in the increments of those vectors, then it starts to make more sense, because it's saying that if I were to go to the coordinate 2, 5, in terms of I and j, that go 1, 2 of those i's, and up 1, 2, 3, 4, 5 of those j's, right? If I'm going to do that same movement, if I'm going to 2, 5, with this new, really transformation matrix, but it's really the new basis. What I'm saying is I need 2 movements in the shape and length of vector 3, 2, followed by 5 movements in the shape and length of negative 4, 1. All right, so it's really just giving you your steps. I kind of equated a little bit to standard deviation. You know, so how big is your movement and in what direction compared to somebody else's movement and their direction? All right. So you have your weights. The weights make up your coordinate in that system, which you're not really going to be able to visualize. The only way you'd actually be able to visualize it would be to generate a new graph paper that is based off of the new vectors, right? So just think of a parallelogram-based graph paper, where instead of having rectangles, you know, as you go out in x and y, you have rectangles all over the place. If you want to go 2, 5, you'd go 2 rectangles over, then 5 rectangles, or 5 squares up. You'd have to go 2 parallelograms over with these dimensions, and then 5 parallelograms up. It would not be interesting. At least the part where you're creating the graph paper. Maybe plotting on the graph paper would be fine. I don't know. But it all boils down to this rule: x is equal to beta times x sub beta. All right, the x sub beta, again, is your coordinates, your transform coordinates, the coordinates as if you're living in that alternate reality where the coordinate system has been changed. All right. So oftentimes what we have to do is, given the transform coordinates, make a determination of what the actual real coordinates would be. Right, the coordinates in our rectangular system. Right, so when I'm looking for x, I'm looking for xy. You know, like our good old-fashioned 7th grade xy. Based off of the fact that we have this transformation matrix and these coordinates within that transformed system, right? So that's a little out there, but procedurally, it's actually very easy. Like, to the point where, I don't know, I don't like saying this, but I mean, conceivably, you can get stuff right in this topic without having any idea what you're doing, why you're doing it. You're just doing it. You know, you're like, all right, it says to create that equation. They gave me a beta. They gave me an x of beta. I need x. All right, let me do it. just going to like multiply. Woohoo! Good answer. Yay. Oh, I saw it, but I think I just wrote down whatever two numbers came to mind. 26, negative 26, 1. All right. So again, this forms the basis of my alternate reality. These are coordinates that exist within my alternate reality. So let me see about creating this alternate reality. It's not going to be. So 3, 2, negative 4, 1. Where do I have to go? Negative 20, 26. So all right, and just bear in mind, normally in our standard units, we have the I vector, we have the J vector. Just give you a little sense of scale. All right, so I is changing. I is becoming 3, 2. I am becoming 3. Negative 4, 1 is the other one. Definitely already made my scale too big. All right, so what we would have to do, because J is now this augmented vector, all right? It's larger in size and at a different angle. So I have coordinates negative 2, 5 living in this system. So negative 2, yes, negative 2, 5. Clone. So I need negative 2 of these. And then 5 of these. 1, 2. My angle is going to be slightly off. 3. group. Just ungroup. For it's not going to get me to 1. That's, like I told you, my drawing ability. Even when I use technology, it doesn't always get me where I want to go. Well, use your imagination. This is at the coordinate -26, 1, which would then have the vector -26, 1. All right, so that's a visual representation of it. But I mean, operation-wise, it's really just a matter of multiplying stuff. In the case of A down here, it's saying find the coordinate vector x of beta of x relative to the given basis. So you have your 2 components of the basis. We have the x is obvious. And I need to come up with the x of beta. So in order to do that, there's no matrix division, but there is multiplying both sides by an inverse. Or you could set up an augmented matrix and row reduce if you want, but I know most people are kind of row reduced out. So what you could do, and I think on the next page I ask you specifically to use the inverse approach, but most people, I think, kind of default to that anyway. I mean, unless the numbers are nice enough where you're like, well, I could probably do this faster by hand than it would take me to even type it in. That's the one I just typed in. So 3, -2. So kind of imagine that everybody thinks their universe is the normal universe. So if you go into somebody else's universe, you're like, wow, it's really strange over here. But they're like, oh no, it's perfectly normal. My rectangular, or my Cartesian system has got my I unit, one step in the I direction, 1 step in the J direction. It's just their I is equivalent to 1, -4, and their J is equivalent to 2, -3. But they know this in their mind and intuitively. So when they create a graph in that universe, they're plotting 3, -2, 3 boxes over and 2 boxes down, and drawing a vector to it. It's just their I is worth this much and their J is worth that much, right? So it's a different way of looking at things, but it's not strange to them. It's only strange to us, right? So it's in a different context, a different universe, etc. But that's just the way you have to start thinking about these things. All right. So the next one kind of works the same way. So stars galore. This is a fun one that you can kind of sweat through a little bit. If you figure it out, great. If not, that's all right. I didn't expect you to anyway. We'll go over it tomorrow, though. And then, yeah.